Welcome back to BrainSparks, everyone. Ready for another Beyond the Future deep dive. Great. Today, we're taking you straight to the bleeding edge of robotics. We're talking research so new the ink is practically still drying.
Yeah, it just dropped yesterday
You got it.
in Science Advances, February 19th, 2025.
If you're keeping score at home.
Exactly.
But it's not just any robotics. We're talking soft robotics.
This is the really exciting stuff. Imagine robots inspired by rope artistry, capable of mimicking heart muscles and swimming like a graceful ray fish.
Yeah. You know, when I first saw this, I thought someone had been binge watching nature documentaries and sci-fi flicks. A little too hard.
A little bit, yeah.
But the science here is legit. This paper is packed with fascinating details on a whole new approach to building soft robots. So what's the big deal? Why is soft robotics so revolutionary?
Well, think about traditional robots, often rigid, bulky, and not exactly known for their delicate touch.
Yeah, that's fair.
Soft robotics aims to change that. It draws inspiration from nature. Think octopus arms, elephant trunks, even our own tongues, to create robots that are flexible, adaptable, and that can interact with their environment in a much more nuanced way.
Okay, I'm starting to see the potential here.
Yeah.
But how do they actually make robots soft? What's the secret sauce?
Oh, well, one of the key ingredients is a special material called liquid crystal elastomer, or LCE.
Catchy.
Yeah, very catchy. It's basically a polymer that can change shape in response to heat.
Okay.
And get this, it acts like an artificial muscle contracting when you apply an electric current.
Wait, so we're talking about robots that flex and move based on tiny electrical signals? That's wild.
It is pretty wild.
But how do you go from a squishy material to, actual coordinated movement? That's where the rope artistry comes in.
Exactly. The researchers took inspiration from traditional weaving techniques, think knots, fishing nets, even those intricate Chinese knots, and used them to create complex LCE structures.
So instead of gears and metal parts, we've got woven fibers acting as the muscles of these robots. That's a pretty radical departure from conventional robotics.
Absolutely. Now, to get these robots moving, you need what are called actuators. These are essentially the components that convert energy into motion.
Okay.
And the researchers in this study created a whole range of actuators by weaving LCE fibers in different patterns.
I'm picturing microscopic robot looms just weaving away furiously.
Yeah.
So what kind of weaving patterns are we talking about, and how do they translate into different movements?
So they focused on four main types. First up, there's the double twisting weaving actuator, or DTWA.
Okay.
Imagine two LCE fibers intertwined like a rope. This allows it to both twist and contract, making it ideal for navigating tight spaces or even moving underwater.
Underwater robots made of woven fibers. That sounds like something straight out of a sci-fi movie.
So straight out of a sci-fi movie.
And I bet the weaving makes them super strong too, right?
You got it. They actually found that the DTWA is significantly stronger than a single LCE strand, able to withstand much greater loads.
Okay, that's impressive. What about the other weaving patterns? They each have their own unique moves, right?
Absolutely. Next, we have the circular four-strand weaving actuator, or CFWA.
Okay.
This one's shaped like a woven circle that can shrink and expand radially.
Oh, wow.
Think of it like a robotic iris, opening and closing with incredible precision.
That level of control is mind-blowing. What's next on our weaving tour?
We've also got the orthogonal weaving actuator, or OWA, where fibers are woven perpendicularly.
Okay.
This creates a symmetrical structure that can contract in multiple directions, making it perfect for building a shape-shifting robotic surface.
Lana, a shape-shifting surface. Now things are getting really interesting. Can you paint me a picture of what that looks like in action?
So imagine a surface that can morph from a flat sheet into a dome, then flatten out again, transform into a cylinder, or even take on a saddle shape, all by simply controlling the electrical current flowing through those interwoven LCE fibers.
It's like programmable origami on a whole new level.
Yeah.
And I bet that kind of flexibility would be incredibly useful for all sorts of applications. But let's not get ahead of ourselves. We still have one more weaving pattern to explore, right?
Right. The last one is called the diagonal weaving actuator, or DWA.
Okay.
In this pattern, the fibers are woven at a 60-degree angle. This allows for more complex bidirectional deformation.
Bidirectional, so it can move in two directions at once.
Yeah.
That's getting pretty sophisticated for something based on weaving.
It is, and what's even more remarkable is that this pattern actually mimics the helical structure of heart muscles.
Wow. A robot that moves like a heart. That's both fascinating and a little bit creepy. But I have to admit, I'm dying to know what they actually built with these amazing actuators.
Yeah.
Did they create any actual robots?
Oh, they did. And you're going to be blown away by what they came up with. Let's start with that shape-shifting surface we were just talking about. They actually built a working prototype.
No way. So this thing can really morph into all those different shapes in real time.
It can, and they didn't stop there. They added a passive grid layer for stability, which also allows the surface to manipulate objects by simply changing its shape.
Wait, so it's not just changing shape for the sake of looking cool. It can actually do things with that ability.
Exactly. They demonstrated its ability to grasp and move objects by strategically morphing its surface. It's like having a robotic hand that can adapt to any shape.
Okay, I'm officially convinced that shape-shifting robots are the future.
Yeah.
But I have a feeling that's just the tip of the iceberg. What else did they cook up in the lab?
Well, remember that heart-like actuator we discussed?
Yeah.
The DWA?
Yeah.
They used that to build something truly remarkable, a biomimetic pump.
You're kidding. A robot pump that mimics the human heart. I can't even imagine how that would work.
It's actually quite ingenious. They essentially replicated the heart's muscle fiber arrangement using the DWA. This allows the pump to create both twisting and contracting movements, just like a real heart, to propel fluids.
So they essentially built a robotic heart out of woven fibers. That's insane. But did it actually work? Could it pump fluids effectively?
Oh, it worked beautifully. This biomimetic pump could lift liquid to heights of over 70 centimeters. They even used it to simulate a blood circulatory system.
This is beyond cool. It makes me wonder if this technology could someday be used to develop artificial organs. But let's move on to the next robot. You mentioned something about a crawling robot.
Yes, this one is a real problem solver. It's called the multifunctional crawling robot, and it can do some pretty amazing things. Imagine a robot that can navigate vertical pipes in both directions, move over different shapes, circles, triangles, you name it, and even detect gas leaks.
Hold on, a robot that can climb, squeeze through tight spaces, and sniff out gas leaks. That's like the ultimate robotic handyman. How did they pack so much functionality into one design?
Well, it's all thanks to those clever actuators. They use the CFWA, the circular actuator, for the anchoring units, which allows it to firmly grip surfaces.
Okay.
And for the body contraction, they used either the OWA or the DWA, depending on the type of movement they needed.
So it's like a modular robot with different actuators working together for different tasks.
Precisely. And to prove its real-world applicability, they tested it on a tapering bamboo surface. It navigated it with ease, showing its adaptability to different environments.
Okay, this is all incredibly impressive, but I know we're saving the best for last, right? You mentioned a robotic fish.
Ah, yes, the robotic rayfish. This one is truly elegant. It uses the DTWA, the double twisting actuator, to power its fin movements, allowing it to swim through the water with incredible grace.
It's like watching a real rayfish gliding through the ocean, but I bet it's a lot easier to control.
You bet. The researchers could adjust the robot's speed simply by changing the electrical current and frequency going to the DTWA.
That's amazing. It's like having a remote control for a robotic fish. I can't believe they've managed to achieve such fine-tuned control with this weaving technique.
Yeah, it really highlights the versatility of this weaving approach. I mean, we've gone from robotic hearts to shape-shifting surfaces to underwater robots, all thanks to cleverly woven fibers.
And what's fascinating here is that this is just the beginning. The researchers believe that this technique isn't limited to just LCE. It could be used with other smart materials, opening up even more possibilities for designing and controlling soft robots.
Okay, now my mind is officially blown. We're talking about a whole new paradigm for robotics, one that draws inspiration from ancient weaving techniques and could lead to robots that are more flexible, adaptable, and capable than anything we've seen before.
If we connect this to the bigger picture, it's not just about the robots themselves. It's about the potential impact they could have on various fields. Imagine tiny soft robots navigating the human body for targeted drug delivery, or assisting in delicate surgical procedures, or robots that can squeeze through rubble to locate survivors after a disaster, or explore the depths of the ocean with an unprecedented level of agility. The possibilities are truly endless.
Absolutely. This research has opened up a whole new avenue for soft robotics, and I, for one, am incredibly excited to see where it leads. It's a testament to the power of thinking outside the box and drawing inspiration from unexpected sources.
Well said. It's mind-blowing to think that we're witnessing such groundbreaking advancements in soft robotics right here, right now.
It makes you wonder, What incredible innovations are just around the corner.
It really does. And speaking of incredible innovations, I want to give a huge shout out to the researchers behind this incredible study. You can find a link to their paper in the description below. Make sure to check it out and dive deeper into the fascinating world of woven robots.
And of course, we want to hear from you. What are your thoughts on this groundbreaking research? What potential applications excite you the most? Let us know in the comments below.
We love hearing your thoughts, theories, and wild predictions. And if you're as captivated by the future of robotics as we are, make sure to hit that subscribe button and give this video a big thumbs up. We've got tons of exciting Beyond the Future deep dives coming your way, so stay tuned and keep those brain sparks flying.
Thanks for watching Beyond Technology. If you enjoyed the video, give us a like, leave a comment, and subscribe. And don't forget to click the bell icon to stay updated on the latest breakthroughs, cutting-edge innovations, and the hidden tech shaping our world.